The moment the final pour sets on a bridge or high-rise, it begins to die. Traditional concrete and steel are passive materials. They stand still and take the punishment of the elements until they ultimately fail. Deep inside the matrix, microscopic battles are being lost every day. Changing temperatures force the rigid structures to constantly expand and contract, opening tiny fissures. Water creeps in, carrying corrosive chemicals that chew through the reinforcing steel. The financial toll of this slow-motion collapse is staggering. In the United States alone, repairing moisture-related damage to concrete costs $1 billion every single year. Because these materials cannot tell us they are hurting, we rely on heavy external interventions. Teams must physically inspect endless miles of highway, and when they locate a critical failure, they bring in massive hydraulic equipment to rip out and replace the dead material. We are now seeing a transition to smart materials, infrastructure engineered at the atomic and biological level to independently sense, adapt, and heal. To build structures that survive, the intervention has to start before the foundation even dries. Curing concrete is a volatile chemical reaction, generating immense heat and internal pressure. Historically, builders had to guess its true internal strength by testing separate sample blocks in a lab. Now, engineers deploy structural health monitoring networks. Small, wireless sensor nodes are tied directly into the steel rebar matrix before a single drop of concrete is poured, permanently embedding them into the bones of the building. This animation shows a cross-section of a concrete slab as it cures. Those pulsing nodes are the embedded sensors, constantly broadcasting the internal temperature and humidity. By tracking the heat of hydration over time, they use the ASTM C1074 Waturity method to calculate the exact structural strength of the concrete at any given second. If the core gets too hot, the final structure becomes brittle. The sensors continuously ensure the internal temperature stays strictly below 158 degrees Fahrenheit, preventing microscopic thermal fractures before they happen. Because project managers have precise, real-time data, instead of relying on generic timetables, they can safely remove temporary structural supports weeks early. This eliminates costly construction delays and averts catastrophic thermal failures down the line. Sensing internal stress is only the first step. Some materials are designed to physically react. In the early 1960s, researchers at the U.S. Naval Ordnance Laboratory, shown here, accidentally discovered a highly unusual nickel-titanium alloy they called Nitinol. Nitinol belongs to a class called shape memory alloys. These metals undergo a diffusionless phase transformation. That means all of their atoms shift positions simultaneously to form an entirely new structure without requiring complex mechanical parts or motors. This diagram illustrates exactly how that shift works. At cooler temperatures, the metal sits in the martensite phase, featuring a slanted monoclinic lattice layout. When heated, the bonds snap into a highly symmetrical, rigid cubic structure known as austenite. Because of that slanted layout, the cool martensite phase allows the metal to be easily bent and deformed. But when a heat source is applied, the atoms violently snap back into their rigid, memorized cubic shape, exerting massive physical force in the process. This thermal actuation solves highly complex engineering problems. Boeing tested shape memory alloys in variable geometry chevrons to quiet commercial jet engines, and the medical industry relies on them to create vascular stents that self-expand using nothing but the patient's own body heat. By replacing heavy, error-prone electromechanical devices with purely metallurgical reactions, engineers can design lighter, highly efficient physical actuators driven entirely by temperature. Even with precise sensors and adaptable metals, extreme environmental stress will eventually cause concrete to crack. To combat this, material science developed smart concrete. As this flowchart outlines, smart concrete leverages high self-healing capabilities and nanomaterials to dramatically enhance durability. The first line of defense is chemical. This data chart breaks down the impact of embedding nanomaterials like graphene directly into the mix. The results show a 75% reduction in rebar corrosion, effectively blocking the chloride ions that lead to rapid structural failure. The secondary defense mechanism is biological. During the casting phase, specific strains of dormant, calcium-producing bacteria are mixed evenly throughout the concrete matrix, waiting in suspended animation. When a fissure forms and moisture creeps in, the water awakens those dormant bacteria. As the crack expands, the newly active cells rapidly multiply and begin excreting solid calcium carbonate, generating new rock to bridge the gap. The result is a biological process that closes 88% of microcracks, allowing a structure to maintain 90% of its strength under stress while cutting long-term maintenance costs by 40%. Sensing, moving, and healing represent the three pillars of a unified field known as Material Robotics, a concept championed by researchers at the Massachusetts Institute of Technology, pictured here. The goal is to achieve the high-level intelligence and physical actuation of a sophisticated machine, but do it entirely through material chemistry. There are no batteries to replace, no wires to short out, and no complex motors to maintain. This shift toward material robotics creates active, living systems engineered to outlast the passive monuments of the past. By building with materials that sense and repair themselves, we are designing a world that stays standing without our constant intervention.